I want to start today with a little word association game. It's pretty simple. I'm going to say a word, just one, and I just want you to tell me the very first image that pops in your head. You ready?
I'm ready. Yeah, lay it on me.
The word is chip.
Okay. Chip. I see a potato chip. Definitely. Ideally kettle cooked, maybe with some sea salt and vinegar. A snack.
See, I went in a completely different direction. I went straight to technology.
Oh, okay.
I'm picturing, a silicon microchip, green board, gold pins, that kind of thing.
Makes sense.
But then if I said, I have a chip on my shoulder, or there's a chip in my windshield, or even I need to cash in my poker chips, that image in your head changes instantly, doesn't it?
Completely. And that instantaneous shift, that right there is the fundamental headache of human language.
That's all about context.
Exactly. As humans, we just navigate this effortlessly. We know if we're in a kitchen holding a bag of Lay's, we're probably not talking about semiconductors.
But for a computer.
For a computer, that ambiguity is a nightmare. It's a wall. A computer sees the string of letters C-H-I-P, and it has, zero life experience to know which one you mean.
And that is exactly what we are unpacking today. We're looking at a process called word sense induction.
Right.
It's basically the mission to teach computers how to figure out which chip we're talking about without cheating and just looking at a dictionary.
And to guide us, we're doing a deep dive into this really fascinating paper from 2011. It's by Mariana Apitianaki and Tim van de Cruz.
It's called a quantitative evaluation of global word sense induction.
Yeah.
Now, I know quantitative evaluation sounds a bit dry, I won't lie to you, but stick with us because this is actually a story about a showdown.
It really is.
It's a battle between the way computers usually learn, meaning the local approach, and this radical new contender, the global approach.
A total clash of philosophies. But before we get to the fight, we have to understand the battlefield. Why do we need this word sense induction at all? We have dictionaries, we have Wikipedia. Why can't we just upload all that into an AI and call it a day?
That seems like the logical move, right? The definitions are already there. Someone smart already did the hard work.
But the problem is the wheel keeps changing shape. The paper calls the traditional dictionary method the fixed list of senses paradigm. And the problem is twofold.
Okay.
First, building those lists by hand is incredibly expensive and time-consuming. You need linguists, editors, years and years of work.
And the second problem?
The second problem is the real deal breaker. Language is alive.
It evolves.
It evolves, exactly. If you fed a computer a dictionary from 1990, it would have no idea that cloud means a network of servers.
Oh, that's a great point. It would just think it's the white, fluffy thing in the sky.
Precisely. Or think about the word catfish.
Right.
In 1990, that's a bottom-feeding fish. Today, it's a person pretending to be someone else online.
Or stream, or tweet, or ghosting.
Exactly. A static list just can't keep up with how we actually speak. Language moves way faster than the lexicographers do.
So we need the computer to go out into the wild and learn on its own.
Unsupervised.
It has to read raw text and figure out, okay, people seem to use this word in these 3 different ways.
But how does a machine even start to do that? It doesn't have our life experience. It's never eaten a potato chip. It's never been ghosted.
So what does it rely on?
It relies on the golden rule of computational linguistics, the distributional hypothesis.
Which sounds complicated, but I gathered from the reading it's actually pretty intuitive.
It is.
It's the idea that words that occur in similar contexts tend to be similar.
That is the core of it, yeah.
My grandmother used to say, you know a person by the company they keep. This is just applying that to vocabulary, isn't it?
That's the perfect analogy. If the word bank always hangs out with money, deposit, interest, and teller, the computer infers it's a financial institution.
And if it hangs out with river, water, flow, fish,
then it infers it's a geographic feature. It doesn't know what a bank is, physically, but it knows who its friends are.
Okay, so that's the mechanism. But the paper compares 2 different ways of analyzing that friend group, the local versus the global. Let's start with local, which I understand is sort of the reigning champion.
Right. So up until this paper, most algorithms worked locally, and that means they operate on a per-word basis. They treat every single word as its own isolated puzzle.
So if a local algorithm wants to understand bank, it only looks at sentences with the word bank in them. It just ignores everything else.
Essentially, yes. It gathers all the instances of bank, looks at the immediate neighbors, the local context words, and then tries to cluster them into groups. It's very focused.
But the authors argue it's a bit myopic.
Yeah, myopic is a good word for it.
How so?
It's solving the puzzle of bank without looking at the puzzle of money or river at the very same time. It's creating these little isolated islands of meaning without understanding how they relate to the rest of the language.
It's like trying to understand a suspect in an interrogation room without knowing anything about the city they live in.
That's a great way to put it. It lacks that broader view.
So enter the challenger.
Yeah.
The global approach. This is what Epidianaki and Van de Cruz were really proposing. How is this different?
Well, instead of looking at one word at a time, the global approach build a full-blown word space model.
A word space model.
Yeah, it tries to determine the meaning of a word by comparing it to the senses of other words across the entire body of text, all at the same time.
Wait, simultaneously. Like, it's comparing chip to every other word in the language at once. That sounds massive.
It is massive. It's not just looking at the suspect in a room. It's mapping the entire social network of the city to see where that suspect fits in. The authors called it demarcation.
Demarcation.
Yes. It defines what a word is by establishing where it sits in this huge galaxy of other words. It uses the whole language structure to sort of triangulate meaning.
But how does it actually do that? I mean, that sounds like an unimaginable amount of data to crunch. You can't just draw lines between every single word.
It is some heavy lifting. And to do it, they use a technique called non-negative matrix factorization, or NMF.
Okay, hold on. Non-negative matrix factorization.
Right.
I feel like I need a PhD just to say that 3 times fast. Can we break that down? What's happening under the hood?
We can. Let's just skip the calculus and look at the logic.
Please.
Imagine these massive spreadsheets or matrices. The algorithm builds 3 of them to cross-reference everything in the text it leads.
Okay, 3 spreadsheets. What's in them?
So first, it tracks nouns versus grammar. Like, is this noun usually the subject of a verb? Is it the object? That sort of thing.
Okay.
Second, it tracks nouns versus context words, so the vocabulary that appears nearby.
Got it.
And third, it tracks grammar versus context words.
So it's cross-referencing everything against everything else. The grammar, the vocabulary, the nouns themselves.
Exactly. It creates this triangulated web of data. And the algorithm processes these 3 matrices together to find hidden patterns. They call them latent semantic dimensions.
Latent semantic dimensions.
Yeah.
That sounds like sci-fi, like we're entering the multiverse or something.
It's much more grounded than that. Think of them as flavors or categories.
Okay.
The algorithm might notice that words like bread and cake and recipe all share a similar mathematical dimension. We humans would look at that and label it food. The computer just sees it as, dimension 42, a cluster of numbers that always appear together.
Okay, so it finds these dimensions: food, tech, geography. But here's the part of the paper that really blew my mind. Words aren't simple. Chip can be food or tech. How does the global algorithm separate those layers?
This is the real innovation here. It uses a switching off technique.
Switching off.
It's basically a subtraction method.
Subtraction. How do you subtract meaning?
Okay, think about audio mixing. Imagine you have a music track with vocals, drums, and guitar all mixed together in one file.
I'm with you.
But you want to hear just the guitar. So first, the algorithm listens to the word chip. It finds the loudest signal, the dominant meaning.
Right.
Let's say the data shows chip is mostly used in the computer sense. The drums are really loud.
So it hears the computer drums. It identifies that as sense number 1.
Right. Now here's the magic. It takes the mathematical dimensions associated with computer and it just switches them off. It subtracts them from the word's profile.
It mutes the drum.
It mutes the drums. It's like peeling the outer layer off an onion. And once that computer meaning is subtracted, the algorithm runs the check again to see what signal is left.
And that's where it finds the hidden meanings. That is so cool. It's like, okay, we know you're a computer part, but what else are you?
Exactly. And it keeps doing that. It finds a pattern, subtracts it, looks at the remainder over and over until it stops finding coherent clusters. It just digs until there's nothing left but noise.
The paper gives a full breakdown of this with our favorite word, chip. I have the list right here of the senses the global algorithm found all on its own.
Okay, let's hear them.
Sense 1 included cache, CPU, memory, microprocessor, RAM.
Clearly the computer dimension. That was probably the loudest signal in the text they used.
Then peeled that away. And sense 2 included bread, cake, chocolate, cookie, recipe, sandwich.
There's the food dimension, clear as day.
And finally, sense 3, accessory, equipment, goods, machinery, supplies.
Which looks like a manufacturing or maybe industrial dimension.
It nailed it. That's the crazy part. It didn't just find chip the food. It specifically grouped it with other baked goods and snacks. And it did this without a human ever telling it what a cookie was.
It really shows the power of that global approach. It found the food dimension not just because chip was near cookie, but because chip and cookie both exist in the same global dimension as bread. It used the whole network.
But wait, finding the list of meanings is only half the battle, isn't it? That's the induction part.
Correct. The computer has built its map. The next step is disambiguation. Can it actually use those senses to figure out a specific, confusing sentence?
Right, the test. Let me read this sentence from the paper. An NV Philips unit has created a computer system using RISC chips made by Intergraph.
Okay.
Humans know immediately that's a computer chip. We see Philips, we see computer, we're done. How does the algorithm know?
It uses a process called folding in.
Folding in,
Yeah.
like baking. Fold in the cheese.
Oddly enough, yes. It takes the context words from that sentence, words like computer, system, digital, processes, and it folds them into that massive semantic space we talked about.
So it projects the sentence onto the map it already built.
Exactly. It creates a semantic fingerprint just for that sentence. Then it compares that sentence's fingerprint to the fingerprints of the 3 chip senses it learned: computer, food, and manufacturing.
And it calculates the difference.
Right, using a metric called the Kullback-Leibler divergence.
Kullback-Leibler divergence. That sounds like a sci-fi weapon. Set the phasors to Kullback-Leibler.
It's basically just a very fancy ruler. It measures the distance or divergence between 2 probability distributions.
So it measures how far the sentence is from food and how far it is from computer.
Precisely. And in this case, the distance to the computer sense was the smallest. The ruler showed they were close neighbors, so it correctly identified that this specific chip was silicon, not potato.
So the theory works, the algorithm works, but the paper is a quantitative evaluation. They didn't just run it on one sentence and high-five each other. They put it in the arena.
They did. They entered the SemEval 2010 word sense induction and disambiguation task.
Catchy name.
It's the Olympics for these kinds of algorithms.
Yeah.
All the research teams bring their best code and compete on the exact same data set.
But there was a catch, right? You mentioned the arena wasn't exactly fair.
This is a crucial point. The data set they used was actually biased toward local methods.
How so?
The data set had a very small number of target words, but a massive amount of context for each one.
Oh, I see.
So it was very deep, not very broad. Local algorithms thrive on that. They love tons of data on a single target. Global algorithms need a breadth across the whole language to establish those demarcations. They were at a disadvantage.
It's like testing a marathon runner by making them do a 100-meter sprint against Usain Bolt. It's not playing to their strengths.
Exactly. But they ran the race anyway, and this is where it gets really interesting. They didn't just enter one version of their algorithm, they entered 2 variants, NMFCon and NMFlib.
Right. Con and lib. Standing for conservative and liberal.
Yes.
We're not talking politics here, are we?
Not quite. We're talking about risk tolerance. It's about how confident the machine needs to be before it makes a call. NMFCon was the cautious one.
Okay.
It would only declare a new sense for a word if the signal was incredibly strong and distinct. It hates being wrong.
So NMFCon is a perfectionist who's afraid to speak up.
And then there was NMFlib, the risk taker. It had a lower threshold, so it was much more willing to guess that a word had extra meanings. It was willing to hallucinate a sense just in case it was right.
So the conservative model plays it safe. The liberal model takes chances. Who won?
Well, let's look at the scores. They used a metric called V-measure. It balances 2 things. Homogeneity, are the clusters pure? And completeness, did you find everything?
Yeah.
The cautious one, NMFCon, failed pretty hard.
Ouch. How bad?
It actually performed worse than the random baseline.
Worse than random. That's embarrassing.
It was so afraid to make a call that it missed almost everything. They just sat in the corner and said nothing because it was waiting for perfect certainty.
But the risk taker.
NMFlib did much better. It scored 13.5% on the V-measure. Now, I know that number sounds low, like an F-.
Yeah, 13% isn't great.
But in this highly difficult task, it was actually a solid score.
Yeah.
It was right on par with the established local systems, like the well-known Duluth WSI system.
So even on a playing field designed for the local guys, the risk-taking global approach held its own.
It did. And when they looked at another metric, the paired F-score, it gets even more interesting. NMFCon, the cautious one, actually had very high precision, 54.6%.
High precision.
Meaning, when it did make a group, it was usually right. It just didn't make nearly enough of them. So it was correct, but mostly useless.
Okay.
NMFLIB balanced precision and recall much better, ending up with 42.2%. It made more mistakes, but it captured much more of the truth.
So what's the big takeaway here? The local approach is the incumbent, perfectly suited for the test. The global approach is the challenger, fighting on enemy turf. And it basically tied.
Effectively, yes. And that is the aha moment for the authors. They concluded that if the global approach can perform equally well on a data set biased against it.
Imagine what it could do on a level playing field.
Exactly. On real-world data raw text from the internet, blogs, news, the global method might actually take the lead. Real language is messy and broad, which suits that big picture model.
It really feels like we're moving from a world where computers memorize to a world where they intuit.
I think that's a fair way to put it. Local methods are about memorizing patterns. I see money, I say bank. Global methods are about understanding the entire topology of the language.
And the authors also suggested they could make it even smarter, right? There was a note about grammar at the end.
Yes, looking to the future. Their next step is to add that grammatical dependency information into the disambiguation phase. In this paper, they only used it in the learning phase. If they can bring that grammar logic into the final decision, that could be a game changer.
It's fascinating stuff. It makes you appreciate how complex our brains are that we do all this instantly.
Without even blinking.
So to recap for everyone, we've learned that static dictionaries are out and these word space models are in. We've learned you can find the meaning of a word by switching off its main definition to see what's hiding underneath.
And we've learned that sometimes being a liberal risk taker, at least if you're an algorithm, pays off more than being a conservative and playing it safe. You have to be willing to be wrong to be right.
Definitely. Before we wrap up, though, this whole conversation has got me thinking about something bigger, a bit philosophical.
I love a good philosophical ending. Go on.
We're teaching computers to define chip by comparing it to bread and CPU. We're defining love by comparing it to affection and hate.
Right. It's all relational. It's a web of connections.
So, if a computer learns the meaning of a concept by perfectly mapping its relationship to every other concept that exists, does it understand it better than we do?
That is the ultimate question, isn't it? As humans, we feel meaning. We taste the salt on the chip. We feel the heartbreak of love. The computer only knows the geometry of where those words sit in space. It has the map, but it's never walked the territory.
But if the map is perfect, does the feeling even matter for the definition?
Or is the feeling the only thing that really matters?
Is true understanding just connecting enough dots? I'm going to be thinking about that all week.
Me too. It really blurs the line between calculation and comprehension.
On that slightly existential note, that's it for this deep dive. Thanks for listening. Thanks for learning with us, and we'll catch you on the next one.